In this paper, we introduce a new optical flow approach termed FlowDiffuser. Optical flow is a fundamental task for video understanding and analysis, which aims to estimate the pixel-wise motion field between two video frames. In the deep learning era, the optical flow methods are typically formulated as discriminative models like CNN-based regression or transformer-based feature matching. Nonetheless, these models primarily learn the input-output mapping, relying heavily on data, and often fail to grasp the nuanced data distribution of motion vector fields. Recently, DDVM has been proposed to address limitations in discriminative models through a generative approach. Despite its simple formulation involving image-to-image translation and its impressive capability to produce uncertainty, its dependency on a standard U-Net-based diffusion model framework substantially escalates computational requirements. Given this, we question the suitability of the standard diffusion paradigm for optical flow estimation. Our aim is to design a model that integrates raft-based models with generative techniques, achieving an equilibrium between the efficiency of conventional models and the advanced capabilities of generative approaches. To tackle these issues, we introduce a novel diffusion-based generative approach, namely FlowDiffuser, which stands as one of the pioneering generative models explicitly devised for optical flow estimation, integrating the strengths of conventional flow models into the diffusion modeling framework. In the proposed paradigm, prevalent modules in the raft-like recurrent decoder are effectively combined with a diffusion-based approach for flow distribution learning. Specifically, during the network training phase, we employ a standard diffusion forward process to create noisy flow fields derived from the ground truth. During inference, the reverse process of diffusion model can be formulated as non-Markovian generative processes. Notably, here our model is set to predict x0 for easily compatible with the flow network, and leverages the deterministic generative process as in DDIM paper. A critical element in diffusion model is the time embedding function, which is essential for synchronizing the diffusion process iterations with their respective time steps. In our model, embedding enhancement module is designed to significantly augment the impact of time embeddings. A fundamental challenge in standard diffusion models lies in their requirement for an extensive series of denoising steps to effectively convert noise into a target signal. To alleviate this issue, we propose a hidden state denoising method tailored for the reverse process in raft-based diffusion models. The key idea is to fully exploit the property that executing the reverse process merely requires an approximate prediction of f0. The training objective is defined in accordance with the typical formulation for supervising f0. Experiments on challenging benchmarks, including Sintel and Kitty, demonstrate the effectiveness of our FlowDiffuser with superior performance to existing state-of-the-art models. Moreover, as shown in Table 2, we conduct experiments to demonstrate that expanding the training dataset positively affects FlowDiffuser's effectiveness. The incorporation of a more diverse dataset allows FlowDiffuser to better capture various patterns and variations, leading to notable improvements in multiple evaluation metrics. In Table 3, FlowDiffuser variations demonstrate exceptional performance in generalization evaluations, consistently outperforming baseline models across all metrics. The proposed FlowDiffuser demonstrates the advantages of effectively capturing uncertainty and ambiguity, similar to DDVM. Additionally, our model's predictions exhibit significantly improved stability, making them more reliable for real-world applications. To sum up, to the best of our knowledge, we are the first to devise a task-specific generative model for optical flow estimation. Besides, we propose conditional recurrent denoising decoder with hidden state denoising approach to improve the performance of flow generation and the efficiency during reverse process. Our FlowDiffuser consistently achieves state-of-the-art results on widely used benchmarks. We hope our work will offer a fresh perspective in rethinking the design of optical flow models. That's all, thanks for your listening.